All right, so what we're doing is we've got our speed of sound, okay, and air column resonance lab. Okay, we learned about standing waves and closed air columns and open air columns the other day. Okay, so when a sound wave travels down a closed pipe, the incident wave reflects off the end of the pipe, or if it's full of water, off the water. Okay, and back towards the source. The interaction of the incident and reflected waves sets up an interference pattern inside the pipe known as a standing wave. All right, so we talked about that. Okay, that's just kind of the background. If this is our closed pipe, the first sound that we would hear would have a standing wave pattern that looks like this, where there is 1/4 of a wavelength in the tube. Okay, we would hear a second resonant point when there is 3/4 of a wavelength in the tube. Okay, and we would hear a third resonant point, okay, when there is, oh, that didn't turn out very well. Whoa, 5/4 of a wavelength in the tube. Sorry guys, that one, yeah, it got kind of psychedelic there. Okay. So anyway, those are the 3 resonant points that we're likely going to be dealing with, okay, with the equipment that we have. All right, so that standing wave can be used to determine the wavelength of the sound. Okay, the universal wave equation relates the speed v of a wave to its frequency f. Obviously, this is the universal wave equation, v equals f times lambda. Okay, wavelength is determined from the length of the pipe because we know how much of the wave is in the pipe at the 3 resonant points that we are going to discover. All right, so the problem is already written for you. You don't need to write it out again. Okay, how can a closed pipe resonance system be used to calculate the speed of sound? All right, so we got to look at our variables here. So the experiment's going to work like this. We're going to have the resonant pipe. Okay, we're going to have the tuning fork, and we're just going to hold the tuning fork, and we're going to move the length of the tube. Okay, so our manipulated variable here, okay, is going to be our frequency, okay, because we're going to be comparing 2 different tuning forks. Okay, we want to see if we get the same speed of sound, okay, for both of the tuning forks. Okay, there's a couple of responding variables. All right, I want you to think about what they are. Okay, as I strike the tuning fork, okay, I'm going to change the length of the tube, right? So the resonant points are going to be determined by what frequency of tuning fork I'm using, okay? And that length of the pipe is going to be used to determine something else that's part of the universal wave equation. All right, so that can help you with your responding variables. There's 2 of them. Controlled variables, anything that remains the same. The thing we're trying to calculate is actually a controlled variable. Okay, we're trying to calculate speed of sound. It needs to stay the same. Okay, if it doesn't, we're going to get some really wonky lengths because they're going to change all over the place. Okay, so that one definitely needs to stay the same. Okay, anything that can affect the speed of sound also needs to be controlled. So I want you to think about what other things might affect the speed of sound that could be present in this room that are not going to change throughout the experiment. They are environmental. Okay. All right, for our hypothesis, okay, we need to generate a hypothesis, if and then statement, okay, that explains how closed pipe resonance can be used to calculate the speed of sound. So the if part, okay, of our hypothesis, right, should talk about standing waves, okay, and how they essentially work inside of a closed pipe resonance system. Okay, so waves are going into the pipe. What are they doing? They're coming back out. Okay, what are they going to produce? That's the if part. Okay, the and, so standing waves. Basically, you're telling me how this works in the if part. Okay, tell me how standing waves and closed pipe resonance works. Okay, and here's a big hint for you. It's up here, and you can probably find it in that part. Okay, you can kind of restate some of the background information that's up there. Okay, the and part's just describing the experiments. Okay, so the length of the different resonant points is going to be recorded. Okay. The then part needs to tell me how you're going to calculate the speed of sound using that data. So basically, how did you solve any of the problems we did on air columns and standing waves yesterday? Okay, that would be the then part of your hypothesis. All right, so our procedure, okay, we've already kind of seen this. I did it for you the other day, okay, where we had the tuning fork and the closed pipe system. So that's all going to be done by me, right? But we're going to have the tuning fork, we're going to have the pipe, we're going to have the water, okay, and we're going to be measuring all that. So we don't need to worry too much about the procedure here, okay? We just need to be able to fill in, okay, the recordings that we make here. All right, everybody with me so far? All right, so are there any questions on the design and hypothesis before I start the procedure? No? Okay. I'm just going to pause the recording here because you guys are going to pop up on the... All right, so what we're going to be doing is filling in this chart, okay? And I'm going to do the experiment here on the screen for you. Okay, no, that's not ideal, but it's what we got. Okay, so we're going to start off with this tuning fork here, right? And the frequency, I don't know if you guys can read it, okay? 523.2, okay? 523.2 hertz is the frequency that we're going to be starting with. Okay, so we're going to go back to here, okay? And our first frequency is going to be 523.2. You guys can obviously type that in, right? So now we're going to get the length of our resonant points here. Okay, so I'm going to move closer to the microphone so hopefully you can hear these. Okay, and I will get our points for us here. Oh, that didn't work very well. Hang on. I had it on a padded surface. That's better. Okay, definitely got louder there. Okay, that length is 0.156 meters. Okay, so okay, so that's our first resonant point, 0.156 meters. Okay, let's go to our next one here. Okay, I think I found it. I'm just going to restrike the tuning fork because I actually touched it against the top of the tube. Okay, I think that's it there. Okay, and we are looking at 0.480 meters. Seems a little high. I'm going to try that one again just in case I missed it. Hang on. No, we're going to go with that. That's what it was. Okay. And now we're going to find the third point. Okay, sorry. Go back to me again here. Okay. Okay, that's it there, and it's at 0.806. Okay, so 0.806 for that one. Okay, so those are our three for the first tuning fork. All right, questions so far, guys? All right, I'm gonna go back to me again here. All right, now we're gonna use our second tuning fork. Okay, and our second tuning fork, okay, 440 hertz. Okay, 440 hertz. Okay, got it there, and we are looking at 0.185 for our first point. All right, so this is 440, and this is 0.185. All right, let's see if we can find the next one here. Okay, I'm just going to check that one again. Okay, I think that's it. We are looking at 0.571. For that second point, and we'll try and get the third one here. This one might be a bit tough for me because it's going to be above my head. Oh, that wasn't a very good straight. Okay. All right, and that one we're looking at 0.949. Okay, so now we've got all of our data. Sorry guys, I forgot to go back to me doing that. Okay, I think you got what you need there. Okay, so 0.949 is our last point there. Okay. So now that we've got our data, let's just quickly look at what you've got to do with it here. Okay, so for the analysis, in terms of wavelength, how far is each of the three resonant points from the reflecting surface of the water at the bottom of the air column? All right, so in answer to that question, I refer you to the three diagrams I drew at the beginning. Okay, that's what they're talking about. How many wavelengths is it for each resonant point? Okay, so they're talking about those three diagrams right there. You're welcome. That's some freebies for you. Okay, I'll go back to that in a minute. Okay, for question number 2, calculate the wavelength of the sound from the tuning fork for each resonant point and show your work. All right, so I'm going to want to see your work in there. Okay, if you're doing it on paper, then snap a picture and insert it. Okay, into the Google Doc, please, not as a separate JPEG file. Okay, put it right in the Google Doc. So I want to see your calculations for each resonant point for each tuning fork. So you're going to have, 6 calculations in there. Okay, showing me what the wavelength is. Okay, then calculate the speed of sound for each wavelength. For each of the wavelengths that you calculate. Okay, again, show me your work. I'm going to want to see that. okay, when you calculate the wavelength for the different points, so this is question number 4, okay, do the answers agree? If not, what might cause the differences? Okay, so when we do those calculations, obviously we should get pretty close to the same wavelength. Okay, we know that because we've done it before. Sometimes we're out a little bit. Okay, so this is kind of a, in preparing you to do your evaluation sources of error part. Okay, so that's kind of what number 4 is looking for. Okay, and then for number 5, why do you start with the column of error being really short as opposed to really long? Okay, there's kind of a very logical reason why we start with the shortest one and move up from there. Okay, you guys can kind of think about that one and give me just a short written answer, okay, on that one. Then, as always, conclusion, copy paste your hypothesis. Were you able to calculate the speed of sound? Was it reliable? Okay, consistent, okay, that kind of stuff. And then for your evaluation, 2 sources of error, how they affected the lab, and how you might improve those, okay, to eliminate them. Okay, all right, questions on what you're doing there? All right, you got the rest of class to get that finished. I think you shouldn't have too much trouble with that. Okay? If there's questions, just let me know and we'll go over them together. Okay?